Okay, fine. So let us start now. So if you remember in the last class, we were discussing parameter estimation problems. So, so in particular, we had considered several kinds of probability distributions, mostly Bernoulli distribution, binomial, Poisson, etc., and also categorical and multinomial distributions. So, so we had seen that all these distributions, they have different kinds of support sets. They have are characterized by PMA for probability mass functions, and each of them they have certain parameters. So now suppose what typically happens is that we have data, we have observations. So like suppose we are given x1 x2 up to xn. So now what we try to do is that we try to imagine that these the observations that we have got are like not some just values, but they are the realizations of some probability or some random variables. Why do we think so? Because like it helps us to make some it helps us to create a probabilistic model, which in turn helps us to make the predictions and various other kind of analysis which we had discussed in last Monday's class when we had talked about some various template problems in earth sciences. So, so now let us consider a case where we are given n observations. So now these observations, when we say that these observations are actually instances or realizations of IID random variables. So we just assume that that this first observation x1, this is there is a random variable which we may call as, let us say, capital X1. Similarly, there is for this x2 there is a some random variable which is small x2 and so on. And finally, there is another random variable which we call as capital Xn. And these values which we have got are simply the realizations of these random variables. We further assume that they are IID, which means what? All of them follow the same distribution with the same set of parameters. So let us say that xi follows some distribution f with parameters p. Okay, so f is so any distribution and p is the set of parameters. So if f is the Bernoulli distribution, then p will have to be the Bernoulli parameter. If f is, say, the binomial distribution, then again p will have, like, p will be not a single thing but two things, right? N and p. So so p by p I just mean parameter or parameters. So now the question is, what is f and what is this p? Okay, so now the first task is choose the suitable distribution f for them. Now what is f? So so part of the hint will come from the nature of the variables themselves. That is, so we, for different distributions, we have already seen what are their support sets, right? So like for example, we already know that for Bernoulli distribution, it has the support set of 0, 1 binary values. For binomial distributions, it's like numbers, and Poisson it's also, and so on. So depending on the uh, kind of the observations we have, we will be able to understand these observations lie within the support set of which kind of probability distribution. So if our observations are as follows, say head, tail, head, etc. So then clearly we understand that like the observations are binary. Okay, so, or otherwise we may like suppose our observations are like 3, 7, 2, 5, 4, 0, etc. Then we say that they are like basically they are integers. If our observations are something like uh, H, F, A, F, H, etc., then we understand that like it's like these are some discrete values. And finally, it may also happen that the observations we have got is something like minus 3.3, 7.2, minus 0.5, 16.3, etc. So these are like real numbers. Fine. So now, whichever distributions we choose, the support set of that distribution has to be consistent with the nature of the data which we have. So if this is the nature of our data, I mean clearly that whatever distribution which we have to use as f, that will have a binary support set, right? So probably we'll go for Bernoulli distribution. But if it's the second, or the like if it is the second case, like we find that the observations which we have got are integer valued, then we may want to go for some distribution whose support set is the integers, like let us say maybe binomial, maybe Poisson, or something else. Okay, if it is only Poisson, sorry, if it is only positive integers, then we may as well go for this geometric distribution. And on the other hand, if we see these kinds of like discrete variables, one thing which we can do is we can think of mapping these discrete values to integers and then just use this binomial distribution, but that may not be very suitable. That is like binomial, in case of binomial distribution, we like it's true, its support set has is the set of integers, but it has a specific meaning. But in case of this, like if we have just discrete values like this, then like mapping them to the two integers may not catch that, or like in a sense is not a very appropriate for the binomial distribution. So in this case, we may want to go for as the discrete distribution, right? This kind, or the categorical distribution, whatever you call it. And finally, if we see that they are like real numbers, then of course we will have to go somewhere beyond these discrete distributions. So we'll have to go for continuous distributions, like say the Gaussian or normal distribution, and as follows. So that we will see a bit later. So for the time being, let us say that we, by looking at the type of the observations we have like we will have first have to choose which distribution f to go for. It may also happen that there are multiple candidates, like for example, for if we see that they are integer valued, then whether to go for binomial or Poisson distribution, that is a choice which we have to make. For continuous values also, we will see that there may be situations where there are multiple candidates which have like whose support set is consistent with what the data we have got. So in such a situation, another thing that helps us is the histogram of the distribution. So like when we whatever observations we have got, we can always plot a histogram of it, right? So like the histogram may look like this. That is, suppose we have got only binary data h and t, right? So we, like if we plot it, we may find that the this is like the histogram looks somewhat like this. Now if we have got real valued data, then we may plot the histogram, and like you know how to plot the histogram of real numbers. So maybe the distribution will look somewhat like this. Maybe something like this. So you will have to find a probability distribution whose PMF or PDF can resemble this kind of a histogram which you have got. Because as we have discussed in the last class, there we have the law of large numbers. The law of large number, of course, the weak law of large numbers we discussed, that is says that if we have as the number of samples approaches infinity, as n tends to infinity, what happens that the sample mean, which is the mu x, or like x bar if you want to call it, yeah, Just a second. So like if we call the sample mean x bar, this approaches the expected value of the random variable. This is the law of large numbers. Now with based on similar arguments, it can also be shown that as the number of samples approaches infinity, the histogram of the observations should actually approach the probability mass function or probability density function of the corresponding random variable. So accordingly, if we plot the if we assuming that we have enough data, and then trying to if we construct the histogram of our data or observations, we have to find such a distribution whose PMF or PDF resembles that histogram. Okay. So based on this, all these so based on the support set and based on the histogram, we will be able to decide what distribution we should use. That is what this F should be. So like for some candidates of that we have already shown. But apart from F, there is something more to it. What is that? These are the parameters P, right? So what do we do with these parameters? From where do we get from? So for that we need the parameter estimation, right? So that tells us that, or that is the where we need to estimate the values of the parameters. If we are going for the Bernoulli distribution, then what should be the value of P? If we are going for the binomial distribution, what should be the values of N and P? If for Poisson, what's the value of lambda, etc. Right? So that's the question of parameter estimation. Now, how to solve this question, how to answer this question, that also we saw in the last class. So if you remember, we saw maximum likelihood estimate. The approach of it is as follows. So we write down the joint PMF and or the PDF of the observation. So far we have not come across PDF. Let us say only PMF. So we write down the joint probability mass function of all the observations. So we remember we have got so n observations correspond which we are imagining have come from n random variables, and the names of those random variables are capital X1, capital X2, capital Xn, etc. So this is the event that these random variables have got these particular realizations. So the probability of this event is, of course, because we have assumed that these are independent and identically distributed. That means what? Because so we know that whenever we have uh, independent random variables, so if we have P, A of B and C, the joint distribution of three random variables which are independent of each other, this is the sign of independence, then we know that we can write it as P of A times P of B times P of C, right? Where these are these are called the marginals. That is, if the random variables are independent of each other, then the joint distribution is nothing but the product of the marginal distributions. Okay, so these are the margins. So we write it as the product of these marginals in this way. Now this marginal, this comes from, this is basically the PMF or PDF of whatever distribution we have already chosen. So remember, we have already assumed that all the random variables, they undergo or their realization of all the observations, they are the realizations of IID random variables, and those random variables undergo this distribution, some distribution F which we have already chosen, and the using the parameters P which we do not know as of now. Okay, so now what we have to do, so this is the joint distribution of all those random variables. Now what we have to do, this is something which we call as the likelihood function of the parameters. So if we write down the probability mass function of this, of whatever probability distribution we have chosen, we will see that PMF will contain two kinds of variables. One is these values, these X, and the others will be the PMFs P, the parameters P. Now these values, these are something which we have observed. These are our observations. We already know them. We are assuming that they are realizations of a random variable, but we know them. So they are constant. We cannot change them. The only thing that is not constant now are the parameters. So what we now have to do is we have to estimate. So basically this thing now, it's a function of the parameters. And so we call it as the likelihood function of the parameters, right? And we denote it like this. If necessary, we can also consider the log likelihood. So now that we have got, or we have got an like we have been able to write down the this likelihood function of the parameters, what we have to now do is we have to choose the parameters in such a way such that this likelihood is maximized. Now why do I want to maximize the likelihood? Because doing so also means that the probability of this event is maximized, because the likelihood function of the parameters is nothing but the probability of the event that has been observed, right? And so since it has been observed, it must be having a high probability, otherwise how would we observe it, right? So based on that logic, of course I mean that's not necessarily the case. Something which is very rare can also be observed, but if since we have got a large number of observations, like everything is like the entire thing is based on the assumption that n is large enough. So if n is small, then all these things will not make any sense. So in that case, we have to do something else. But assuming that n is large enough, we can assume that the event that we have observed is a fairly common event, and hence its probability also must be high. So using that kind of a logic, we try to find that value of the parameters which maximizes the likelihood function. And that the way to maximize the likelihood function is, that is, we differentiate the likelihood function with respect to p. I mean, if there are multiple parameters, then we partially differentiate them to each of them. If there are constraints, then we bring in those constraints through Lagrangian multipliers and other mathematical tricks. We equate those derivatives to 0, and then we solve the simultaneous equations and get the values of the parameters. So though what we get that way are the maximum likelihood estimate, or MLE, of the different parameters. And so some in the last class we saw the examples of such maximum likelihood estimation also for Bernoulli distribution, for Poisson distribution, etc. Now let us come back to the case where the observations which we have got are the real numbers, right? So in case they are real numbers, so we have to go for continuous random variables. Or so continuous random variables are those whose support set are continuous. Like, so they may be like in some cases they may be all the real numbers. In some cases they may be the positive real numbers. In some cases they may be real numbers within a particular intervals. In other cases it may even be, they may be real valued vectors also. So like, so in this case, of course, there will not be probability mass function. Instead there will be probability density function. So what is a probability density function? So so suppose you have a function f and which and you have the random variable in question is, let us call it as x. Okay, so now for f to be a valid PDF, the following conditions will have to be satisfied. Fx should be greater than equal to 0 for all x in the support set of this thing, of the random variable that we are talking about, right? So if this is if the random variables support set is the entire real number, then like x can also be any real number. I mean, this condition must hold for any real number. If the support set is, say, a particular interval, let us say from -1.5 to 7.3, If that is the support set, then for every x within that interval, this property must hold. If it does not hold beyond that interval, it's not a problem. But within that interval, it must hold. Also, like if we carry out the integration over the support set, then we should get 1. Okay, so that is what is called the this thing, the probability density function. So it basically means that, like if you like, so suppose this is the like let us consider such a random variable whose support set is from a to b, where a and b are any real numbers. So then the PDF would be some function like this. It may be some function like this. It's not going, it will not go negative anywhere. It's either 0 or positive. So that means what? So from so this tells us that if we consider any particular point, like define a probability is in this case a probability at a given point, we do not calculate or we do not talk about it. But in fact, we can say that the probability that the random variable will take exactly some particular value, like say like 1.6. That is, if the event is the random variable takes this particular value, then its probability will be equal to 0. It has no mass at that point. It's because it's a continuous thing. So here the mass has to be considered in small intervals. So we say that something like, if we say that the probability that the variable lies within a small interval around the value which we are interested in, if it is something like this, right, then we can say that the probability of this event. So can you tell me what is the probability of this event, if assuming that this function is called f? Yes. Anyone wants to say?
Area under
Area
the,
yes, area under the curve. So what is the expression for that? The area under the curve, does it mean the area under the entire curve from here to here?
no, between the
between that interval, right? Between the
1.6
yes.
and
Yes. So what is that? So what is that? That is correct. So basically we can like draw some kind of a rectangle like this. So like this end is 1.6 minus delta, and this end is 1.6 plus delta, right? So what is the width of this? So basically, so as you said correctly, the probability will have to be the area enclosed by the curve and these two lines. Now since delta is very small, we can assume that the curve is almost horizontal here. I mean, it's actually not, but we can just assume. And then so the area of this rectangle will be this height times this breadth. So what is this width? This width is of course minus lambda 2 plus lambda. So it is 2 lambda times what? 2 lambda times what? Come on, quick. This is basic stuff.
if we assume if we assume it is necessarily a thin strip, we can take that f as a f at 1.6.
Right. So you just by assuming that this is very small, it is infinitely small. So we can assume that the like this is this is completely horizontal. So that means this height is going to be f of 1.6. So this is the probability of the whole event. So probability and PDF are different things. Probability now that is the, like, if we are looking for probability of a particular event that the random variable lies within a particular interval, that we can calculate from the PDF using this kind of calculation. But of course, now of course, if like suppose delta is not an infinitely small thing, right? So suppose I want that what is the probability that x lies between, let's say, 1.2 and 1.8, right? So obviously in that case, as we know, in that case we will have to, the entire area from 1.2 to 1.8, it will have to be divided into infinite number of such, or as many number of such rectangles as necessary, each of which are infinitely small width. And so what we will finally get is basically the integration of fx from 1.2 to 1.8, right? This is the probability of the event, right? So this is the, like basically this is the story of the probability density function. Now this probability density function will, the nature of this probability density function will vary from one distribution to another. So if we first of all, so here are a few sample continuous distribution. Not all of them are like the there are of course more continuous distributions like that. So let us first of all consider the case of beta distribution. Okay, so beta distribution, its support set is from 0 to 1. Okay, so so if we plot its PDF, it's
కాలుతుంది చేపట్టద్దు అది ఉల్లగండి.
So the PDF here, if we want to plot it, let us say I'm plotting the PDF between 0 and 1. So you can see, in this case the PDF may look somewhat like this, or it may also for a given set of parameters it will look like this. For another set of parameters it may look, let us say, it may also look like this. For yet another set of parameters it may look like this. Okay, but for but whatever it is, it will roughly be this kind of a curve, that is from, it will be before 0 it is 0, it's the PDF is 0, then it gradually rises, it reaches some kind of a peak, and from there it again comes down till 1. Now exactly where that peak will occur, that is that depends on the parameters. Okay, so now let us see what exactly is the PDF in this case. So the PDF of the beta distribution is given as something like this. So there are two parameters, A and B, both of which are like numbers, I mean integers, positive integers. Okay, so it's like let us say A and B are two positive integers. So they, like we say that they are part of Z plus. So the PDF is defined as fx is equal to x to the power a minus 1, 1 minus x to the power b minus 1. Okay, so when what is this? This as like this is what is called the beta function. Beta function. What is the beta function? Some of you may have already studied it in some mathematics class. So we define beta function in the following way. Beta function takes two integers as parameters, and it is defined as this is like this is the beta function. This is a definition of the beta function. Okay, so when I claim that this is the PDF, So first of all, you will have to check whether it is. First of all, you check whether this satisfies the PDF conditions of PDF or not. So what is the condition of PDF? Like in its support set, it has to be non-negative, and its integration over the support set will have to be equal to 1, right? So for that, let us check the first criteria. If we come to the numerator, so x is some value between 0 and 1, and 1 minus x will also have to be some value between 0 and 1. Both are being raised to some integer or maybe 0. So obviously the numerator will have to be positive. What about the denominator? So the denominator is the beta function, and because of the nature of the function, you can understand that this will also have to be positive. So yes, so like this cannot be, and so the its PDF is definitely non-negative. And then is its support equal, is the integration of its support equal to 1? So as you can understand, it's actually tailor-made to be that only. So if you, so beta of a comma b, the denominator is of course a constant quantity. If you integrate this over the entire domain, over the entire support set, which is from 0 to 1, then basically then you are integrating the numerator from 0 to 1, in which case of course the numerator becomes the same as denominator. So of course that integration will be equal to 1. So this is also correct. So now the only thing that remains unanswered is what are a and b. Okay, and you can actually try out different values of a and b. So like for example, if it is like let us say, I'm just saying a equal to 4, b equal to 2, let us say. Then what happens? You will see that that is, it will fail, the peak which we are talking about will lean somewhat towards 1. Okay, so like for example, I am not saying in this case it will be exactly like this, but this plot where the peak is tilting towards 1, this kind of a thing may be observed if a equal to 4 and b equal to 2. But if both of them are equal, let us say a equal to 5, b equal to 5, or maybe a equal to 3, b equal to 3, then we will see that the peak is like in between the like exactly halfway. That is, it is achieved at 0.5. But then what is the difference between a equal to 5, b equal to 5 and a equal to 3, b equal to 3, or for that matter a equal to 16, b equal to 16? The difference is the height of the curve. So it's like in one case it will be a like a like it will be a gradual and slope and a steady peak around 0.5. Then as we increase this thing, we will see sharper peaks, sharper and higher peaks, right? We will see these kind of structures. Okay, fine. That is at the extreme case, like we will see a peak at exactly 0.5, which is like infinitely tall, and but it is just at 0.5. Then like that is achieved at as a and b tend to infinity. But for small values, we will see it's like a flat kind of thing. Okay, it may be that like from 0 to 1, we see a very gradual rise, and then it comes back like this. Okay, then for like for slightly higher values, we see a sharper, that is it remains slow, it remains low for a lot longer duration, then it makes a sharper rise towards 0.5, and then again it makes a sharp descent, etc, etc. See, on the other hand, if we are talking about a situation where maybe a equal to 2 and b equal to 7, something like that, then we will see that the peak is shifting on towards the left side. So this may be a possibility. Okay. So now, so this is the story of the first distribution, which is the beta distribution, the first continuous distribution. Then another distribution which is often used is the gamma distribution. So gamma distribution is often used like this is defined for positive real numbers. That is real. That is from its support is basically from 0 to positive infinity. So in this case also it has two parameters, alpha and beta. So in this case the two parameters are called the shape and the scale parameters. Okay, and this is what its PDF looks like. Okay, and if you plot the PDF in case of gamma distribution, so obviously like as you can understand, so like from 0 onwards like for all positive values of x, the PDF will have some values, unlike beta whose PDF is limited between 0 and 1. Here from all positive values it has some PDF. So typically a gamma PDF looks somewhat like this. Okay, so so like rise, basically what happens is that as you increase the value of x, the PDF rises sharply, very sharply, till it attains a peak, and then it slowly descends, keeps on descending, becomes small but still keeps descending. And like basically and it approaches infinity. So this kind of a distribution is called a long tail distribution. So since this is a class on earth system sciences, so gamma distribution is something which is of particular use to us, because like there are many quantities which we will come across, many kinds of atmospheric variables which have this kind of long tail distribution. Say for example precipitation. So precipitation, as we know, the rainfall at a given location on a given day, so first of all it supports it. Its support will obviously be have to be positive. There is no such thing as negative rainfall. So but it can be zero. It can have some zero value. That is, so we keep as so, but remember that zero is not a support of the gamma distribution. It starts after zero. Zero itself is not part of it. So so those days in which there is zero rainfall, that is dry days, they are not to be included. We have to consider only the wet days in which there is some amount of rainfall. So then if we plot the frequency or the histogram of rainfall on at any given location, you will see this kind of a structure. So that means what? That means the low values are very likely. Which means that whenever there is rainfall on any given day, when there is rainfall, it's usually a low value. Like it can reach up to a particular, like maybe some 5 millimeter or something like that. That may be most frequent. After that, the frequency starts decreasing, but it never becomes like completely zero. That means there can be some days where there is say 30 millimeter of rainfall, which is reasonably heavy, but such days are less frequent. There can be some days where there is 50 millimeters of rainfall, but that is even less frequent. There can be some days where there is like say 200 millimeters of rainfall, which is going to cause a flood. Maybe that will happen in once a year or something like that, but it's not, its frequency is not zero. So like in that case, if we look at the histogram of that kind of a quantity, we will see this kind of a long tailed structure. So that is the long tails. That's for to model such variables we need long tailed distributions such as the gamma distribution. So now, as I said, the gamma, just like beta, the gamma also has two parameters, alpha and beta. So so those are called the shape and the scale parameters. Shape and scale. So what do these parameters mean? What do they determine? They basically determine where the peak is going to be and how high that peak is going to be, just like in case of the beta. Okay. So for like for some values of alpha and beta, we may see the peak is like a very sharp rise to the peak, and then descent from there. For different values of alpha and beta, we may also see different heights of the peak. There can be like a low peak like this, or there can be a high peak like this. And then and then whenever there is a peak, there is of course the question of how sharp its ascent and descent will be. So these are like these kinds of things are taken care of by the by these shape and scale parameters, and also by the nature of the function. So as you can see, this is the PDF. Beta to the power alpha times x to the power alpha minus 1 x e to the power minus beta x whole divided by gamma a, where this gamma a, this is the gamma function. So in case of beta distribution, just like we had the beta function, similarly in case of the gamma distribution, we have the we normalize it by the gamma function. And what is the gamma function? The gamma function is like basically this same thing itself. It is x to the power alpha minus 1 x into e to the power minus beta x integration, like it's like this. So gamma of AB, we usually write alpha beta, we can write it as like this. The integration is from 0 to infinity, means all the positive numbers. X to the power a minus 1 into e to the power minus bx into dx. This is the gamma function. So in case of the gamma distribution, the PDF is defined as just x to the power a minus 1 e to the power minus bx whole divided by there is a another factor also which I just forgot to mention. Sorry, b to the power a, b to the power a or a minus 1, what is it? A only, divided by the gamma function. Okay, so this is about the gamma distribution. And then finally, of course, we have the most famous like continuous distribution, which is the Gaussian or the normal distribution. Okay. Why is it called? Its actual name is like actual scientific name is the Gaussian distribution, after the scientist Gauss who formulated it. But this is also called the normal distribution. Why it is called the normal distribution? Because in various ways it is the standard thing, or the like if we measure any quantity in the world, most likely it follows this kind of a distribution. So this kind of a distribution, it is characterized by, as most of you know anyway, it is characterized by the bell-shaped curve. So what is that bell-shaped curve about? What does it mean? It means, so suppose you are measuring the height of people. Okay. So for that purpose, what you do is you assemble some very large sample of people from different parts of the world. Let us say some 1 million people. Okay. And then you plot their a histogram of their height. And then what you will, of course, I have not seen the results of that experiment, but we can assume in good faith that it will look somewhat like this. Okay, so this like we may get a this peak at maybe about say 5 feet 3 inches or something like that. And then there are of course some very tall people, say, who are like more than 7 feet in height, and then 7 feet in height. Then there are maybe very short people who are say less than 4 feet in height and something like that. But in general, we can see that that is so there is a peak around on both sides of the peak there is symmetry. That is the speed at which it goes up is also the speed at which it goes down. Okay, so this is like so that is what we like. So if we put some kind of an envelope on top of this histogram, what we get is something like this. This is what is called the bell curve or the bell-shaped curve. So this is what, of course, I am talking about is histogram. Now, from histogram, and as we discussed earlier, histogram is related to the concept of PMF and PDF of a distribution. If we assume that that histogram is calculated over a large enough sample of people, which we are assuming in this case like 1 million or something like that. So suppose we have so suppose we assume that the variable in question, namely the height of the people, is actually a random variable x. So on seeing this kind of a bell-shaped curve, we will be tempted to say that it undergoes the Gaussian distribution, which is parameterized by two things, mu and sigma. This mu is basically the peak value, or also called the mean, and this sigma is the variance, or the instead of sigma we can call it like we can just consider the square of the things, that is its variance, right? So the this mean the mu basically indicates where this peak is located, and the sigma square indicates how fast it or how steep the rise and fall of the values are beyond the peak. Okay, so like a large value of sigma will mean that it's spread over a longer region. It is maybe something like this. Right, like this value is, so wherever the peak is, this value is called the mu, and and this width this is related to sigma. I mean, I'm not saying that this width is equal to sigma, that's not the case, but this is equal, it is related to sigma. But if sigma is smaller than this, then we'll understand that it's like its range is shorter. Okay, so that is the reason why this is called the sigma is called the variance. So what is variance? Variance is the square of standard deviation, which we know is a measure of dispersion. It's like the higher the variance of the standard deviation, the more dispersed the distribution is. The more dispersed the distribution, it means a larger range of values has significant probability, right? So in this case, as you can understand, for so if even if you consider a value like this, it will have some or if we consider a interval like this, it will have some probability in the first case, but in the second case it will have almost zero probability, right? So that is like what the Gaussian distribution is. So this kind of a bell-shaped curve, this can be represented by a specific type of function, which is the PDF of the Gaussian distribution. And so we like, this is something which you would have surely studied in statistics, like when you are preparing for your JEE. So this is the equation for the PDF of the Gaussian distribution. Oh, you like 1 by root 2 pi into sigma e to the power minus 1 by 2 sigma square into x minus mu whole square. Right? This is the Gaussian PDF, and you can so this, unlike the first two, this PDF is its support set is over the entire real axis. Any real number theoretically has a has a PDF value under the Gaussian distribution. That PDF value may be very small, it may be something close to 0.0, something close to 0, but it will never be exactly equal to 0. Okay, so and you can like you may try out sometime to work out that if you integrate this from minus infinity to plus infinity, if you integrate this quantity, you will still get equal to 1, which indicates that this is a valid PDF. Okay, so Now this whole concept, the concept of the Gaussian distribution can be generalized to higher dimensions also. So suppose, so what if this sorry. So what if this is not a like what if this the variable which we are talking about, the random variable is talking about, is not a single quantity but like it's a vector. So suppose instead of measuring the heights of people, I am measuring like a set of attributes of the people. Let us say the blood pressure of the people. Let us say their heart rate, their pulse rate, maybe their like maybe their blood sugar level, their also their height, their weight, everything. Let us say so many things we are so many attributes we are measuring for different people. Okay, so for like for every person, like we are measuring 6 different variables. Now this kind of a situation can be seen in two ways. One is that you can just assume that these are 6 different variables, so you will fit 6 different distributions to them. So you can say that for blood pressure, you will like you will separately consider its PDF. I mean, first you consider its histogram. You see that the bell-shaped curve is coming, so you go for one Gaussian distribution. Maybe its parameters are mu and mu1 and sigma1. Similarly, you take this one, the heart rate. You see this is also like it's looking like that only, so you just go for it. You consider another Gaussian distribution but with a different mu and sigma. Similarly, the others also, each of them you consider them as some separate Gaussian distribution which which you can allow different values of the parameters. Right? The problem arises that many of these things are actually correlated. That is, for example, height and weight are certainly correlated. That is, a taller person is generally, this is not always the case, but we can expect that a taller person is probably heavier than a shorter person. Need not be, but is more likely than not. Similarly, some of the other attributes may also be related to each other. So that is to say, if we are considering them as all separate random variables, we may be missing out on various interrelations between them. So to capture this kind of all these interactions between the different variables, we go for what is known as the multivariate distributions. That is, the random variable which you are considering is no longer a single variable but a collection of variables. That's why we are calling it multivariate. And if you think that their joint distribution is also Gaussian, then we can, for that we can go for the multivariate Gaussian distribution. Okay, so so in that case, what it actually means is that instead of considering the only the real axis, let us consider a higher dimensional space. A higher dimensional space might be difficult to visualize initially, so let us say initially two-dimensional case. Okay, two-dimensional. Okay, let us say that there are two variables x1 and x2, and at every point we are plotting the PDF. Okay, so the PDF in that case, so like in this case the PDF will, because the two dimensions represent the two variables, the PDF will of course have to be in the third dimension, that is along the z-axis. So let us say it's something like this, right? So in along the z-axis we have the PDF of x1 comma x2. Okay, so now if we plot the PDF, so obviously it will be a three-dimensional structure, and then you may see some peak somewhere, and I mean this time the peak which we will be talking about is a 3D peak, somewhat like a mountain. Okay, so like you can try to visualize it as well in this way. So like there is it looks like a mountain, and that that peak, that is like in that case the new mu for the for this kind of a two-dimensional Gaussian distribution. Similarly, instead of considering two-dimensional or two attributes, we can consider say 6 attributes, as we are saying in this case. So if you consider that 6-dimensional space, which of course we cannot visualize easily, what it basically means is that the bell-shaped curve which we are seeing in the which we can easily understand in one dimension. So there is, it's like a 6-dimensional bell-shaped curve. That means in that 6-dimensional space there is a peak, and beyond the peak the values go down. I mean the PDF values go down symmetrically in all directions. Okay, so that kind of a so what the distribution does is that it basically attaches a probability value to every point in that 6-dimensional space. I mean the PDF value to every point in that 6-dimensional space, and that PDF value is given by this kind of a complicated expression. But if you look at it carefully, you will understand that this is actually analogous to the to the one-dimensional case. The only difference is that there are two differences. One is that this mu, which is a single number in case of the normal distribution, is now a vector. That is, see, its support set is Rd, that is the d-dimensional real space, and we are doing this operation x minus mu. So if x, that is the measurement, if it's a d-dimensional real number, then obviously the mu will also have to be the d-dimensional real number, otherwise we cannot carry out this operation. So this mu, this is a d-dimensional real number. And then we have this sigma, which is called the covariance matrix. And this is a D cross D real matrix. So what is the significance of that covariance matrix? We will see in the next class. Okay. And in the next class, we will also see that how to do the parameter estimation in case of this kind of real valued distribution or continuous distribution. Okay. So we'll meet again tomorrow at 4 p.m. Thank you.